Saxon Algebra 1, Lesson 87. It's a two-parter, gentlemen. I think we've done these before, but John does this thing. He really goes hard on it in the two levels above where you guys are at right now, in Algebra 2 and in Advanced Mathematics. He'll do multiple topics in the same lesson. I consider that really sneaky. But what he's trying to do is give you baby steps, but sometimes he has to double up on the baby steps in order to get everything delivered to you in the end. So I guess this is the good news, is that when John gives you multiple topics in one lesson, you can be assured that each step is going to be pretty easy because he wouldn't put them together if they were hard. So, and you can tell when there's double topics because I'll write it as A instead of just putting the single topic up there. All right, we've been doing systems of equations. We've seen equations like that in a system, and we've seen things like that in an equation, right? Sometimes we'll see these together. Sometimes something like this will look more like this. We're used to all of that. Now we're going to deal with a different kind of a system of equations. It's not harder, it just looks a little different. The hardest thing about these problems, I think, is reading them because John squishes all the information together on the page. I don't like the way he writes that. I write it differently. What we're going to get is 1, 2, 3, 4 equations. I'm going to write them in a list rather than a row, and it's going to make it a lot easier to wrap our brains around it. So don't panic when you see that long line of gibberish. Just look for the commas, and P.S., once I write this down, you'll see that they all follow the same pattern. Ready? Okay. That's the first one. Okay, so this is our system of equation. It does look a little different than what we're used to. What are these R's and T's about? They stand for rate and time. You don't need to know this yet, but it's helpful just to kind of get the ideas into your head. Okay, we're going to be doing problems where we start with the word problem, and we have to create these equations ourselves eventually. Don't worry, not today. But R stands for rate, T stands for time. The subscripts equal the names of the people. So this might be Elaine and Wally. They would be some serious 60s throwbacks if they were. Elaine and Wally are taking a trip, and we're comparing Elaine's rates and times to Wally's rates and times. All right? So that's all that means. Then we get more information about the rates, and then we get some information here about the times. Now, what do we do with this mess? First of all, we recognize that one of these equations is way more complicated than the other. And it's the first one, right? It's got all 4 of the variables in it, and that tells us that it is what we call the base equation. John does not use that terminology, but I do, because this is the equation we're going to plug everything else into. All right? It's kind of like in our old systems of equations, we'd say, let's plug this into this. That would make this one the base equation. This is more dramatic because we're going to plug all 3 into that. All right? So the first thing that we do, step 1, is we write the base equation with buckets. Are you ready? Okay, so it's this times this equals that times that. So make the buckets big because one of the things that we're going to pour into them is going to be big. Okay, did that. 2. Using the base equation, we're now going to substitute in the other equations. All right, so just like we do with our other kind of substitution, except we're going to do it 1, 2, 3 times. All right, so let's do it the first time. The rate of Elaine is 200. I just made that up, but RE equals 200. You can give names to these people if you want, though. It's more fun that way. Okay, she goes in the first bucket. The rate of Wally goes over here on the other side in the first bucket. Okay, now this is not ready to be substituted, is it? Because we need to have one variable by itself in order to substitute it in. Now, the interesting thing is we can rearrange it either way because we can plug in a TE or a TW, right? So let's just do this. Let's subtract Wally because he's the one that's closer that way. So I'm going to subtract Wally from both sides, the time of Wally. So I'm going to rearrange it so it looks like this. Right? The 9 is positive. We'll be doing minus TW, minus TW. All right? Now we can plug this. That goes right there, right? The time of Elaine. So we'll put 9 minus TW into that bucket. That's why I made it bigger, because I knew one of them was going to be longer. All right. Now we get down here, though, and we don't have anything for the time of Wally. So we just put in that same variable. And the magic that's going to happen is, look, now the variables match, so everything's going to be fine. It will always work out. I didn't have to do anything special to make that happen. Just rearrange this equation for one of them, and then for the one that you don't have, just put in whatever's in the original. If I would have done it the other way, it would work out just as fine. I'd be solving for time of Elaine instead of time of Wally. Okay, so here you can't go wrong. Just subtract one of them. All right, now we're into familiar territory. We're going to distribute 1,800 minus 200 TW equals, and this we don't even have to do anything, just take the parentheses off. We didn't need these parentheses, but back when we were just setting this up, we didn't know that. We didn't know how it was going to work out. So just go ahead and put them in buckets, and then you can rip them off when you need to. All right, let's add 200 TW to both sides. This is just straight algebra. Okay, and then we'll divide by 450. In these problems, John almost always makes the numbers turn out precious and cute. I know that 450 times 2 gives me 900. So if I do that twice, 900 and 900, that adds to this. So that tells me that 450 goes into 1800 4 times. Does that make sense? I hope so. So that tells me that TW, the time of Wally, equals 4 hours, I presume, but we don't really know. That's cool. Now I look back at the problem and say, John, did I do what you asked me to do? He says, find the time of Elaine and the time of Wally. Okay, so then we look back at our equations and go, oh, look, the time of Elaine equals 9 minus the time of Wally. So that means the time of Elaine equals 9 minus 4, which is 5. Okay. What was I going to say about this? I don't remember. There's our answer. Time of Elaine is 5. Time of Wally is 4. Yay, those are the right answers. Okay, so it's just substitution. It's just solving a system of equation that looks crazier and we have to do a little rearranging on, but we've done this before, right? It's not that bad. Okay, substitute into the other equations, and then the last step is just solve. You know how to do all these steps, right? Remember when just distributing was a whole problem, right? Now I'm like, it's one itty bitty step in this whole giant thing. That's because you guys are smart. You don't need little baby problems anymore. Come on, let's do the hard stuff. All right, example 87.2. John is being a fun killer, and I'll tell you why. He didn't give us letters for our subscripts this time. He gave us numbers. Now that's fun because we get to say R2T2, which never gets old. But I'd rather make up names about people's weird, or stories about people's weird names, and we can't this time. So it's R1T1 plus R2T2 equals 360. This looks a little bit different than last problem, but just keep in mind that this has got all four variables, and when we decide on our base equation, we'll take a look at that again. All right, let's keep going. Again, John lists these in a row. I think that's madness. I'd much rather see them in a list. Okay, there's our system. This looks a little different, but we still have R1, R2, and then these two combined. So our process is going to be pretty much the same. It's just that our base equation, which will be this one, that's our base right there. You want to set your base equation right away. It's just going to have a slightly different shape. So let's set it up. R1 times T1 plus R2 times T2 equals 360. Makes sense? There's our buckets. Now we're going to substitute in where we can. R1 is 30, that's right here. R2 is 40, that's right there, so it's this one. Now this time, just for fun, let's subtract T1 instead of T2, just to show you that it doesn't matter. So T2 will equal 10 minus T1. One time, I don't know when it was, you guys, 7th grade maybe, possibly 8th grade, I made a mistake on a test. I was rearranging, just like we did here, only this is what I wrote instead. I somehow decided that I wanted the T1 to be positive, so I was going to make minus 10 instead. It's supposed to be like this. This was me being crazy. And isn't it hilarious that how many years later, I will tell you what, 7th grade, how old was I in 7th grade? That was maybe 1971, right? A lot of you have parents that weren't even born yet. And I can still remember losing a couple points on a math test because I messed up that equation. I remember so vividly me getting back my test and finding that mistake and just being like, oh, that was wrong. Okay, so don't be like me, kids. Do it the right way. All right, so now what we're going to do is we're going to say T2 is what we can substitute for. T2 is in the last blank, so that's here. So I'll write 10 minus T1 there. We don't have anything to put in this blank, so we just put that T1. See how it worked out again? Now we just have two T1s. It's so beautiful. Algebra is so magical. Okay, now this is the one that we don't really need the parentheses on. 30 plus T1 plus, now we distribute, 400 minus 40T equals 360. We can combine like terms at the same time we swim this 400 plain number fish over there. And we're going to have negative central, but that's okay. We can handle it. 30T1 minus 40, I forgot the one, T1 equals negative 10 T1. If we were sitting in the same place at the same time, you guys, I would be doing none of this math myself. You would be working so much harder. So, you know, I know that watching videos isn't always the most interesting or stimulating way to learn math, but you can just appreciate that you're getting a whole lot more rest and relaxation out of it. 360 minus 400. Yell really loud so I can hear you. What would the answer to that be? I'm listening. Louder, I can't quite hear you. Oh, right, minus 40. Good job. Okay, then we subtract by minus, or not subtract, we divide by minus 10. That's gone, and we get T1 equals, let's see, the number will be 4, and the sign will be positive. So T1 equals 4. And then we see right up here that T2, which is the other thing we're supposed to find, is 10 minus T1. So I'm just going to do this, and just to show how I did my work, I'm going to write that 10 underneath. Do you see how that kind of validates how I got this right? If I just wrote that on a test and I just did the mental math wrong and was crazy and just put the wrong number there, that my teacher could not give me any points. But if I did, let's say I accidentally wrote 7 in there, and then I said, oh, look, they add up to 10, that would be the teacher's way of saying, oh, she was trying to make it add up to 10. So show your work even if it's not in the most traditional way. That's the final answer. Yay! Okay, that's our work on system of equations. We're starting working on 4 equation systems where we find a base equation and then we substitute everything in, right? The nice thing about this is John is baby stepping us toward the day when we're going to get the story that goes with this. We're going to have to read the story, write these equations, and then do all of this work. The good news is we'll be used to doing all of this work because we're already practicing it. So then we'll just have to figure out how the story works, but the rest of it will seem super easy. Won't that be fun? Oh my gosh, I can't wait. Part B. Tests for functions. This is another part. This is another baby step that I really enjoy. Okay, we talked about functions as this whole sausage machine thing. Oh no, I didn't really talk about that. It's a machine though, right? Where we have input and we have output, right? And we have a function in here like x minus 2, right? And we'd take all our x values, we'd put it through this machine, and then we'd get our matching y values. And we drew kind of a simplified version of that like this, saying that if we have 3 numbers here, they need to have, there needs to be this mapping, right? And every value over here needs to have one and only one image, we called it, on the other side. 2 has to always yield 3. Obviously, this doesn't work for this. I just made up numbers. We can't have any arrows going like that because that's saying that 2, sometimes it's 3 and sometimes it's 7. No bueno, right? So you learned how to do this. And then you also learned that these also represent pairs of points. This one would be 2, 3, and this one would be 1, 7, and this one would be 0, 6. And that we can look at the lists of points and also check to see if something is a function or not a function, right? So we have 2 different kinds of tests for a function. I call this one the oval test, right? The ovals. And I call this one the pairs test. And now we have what's called a vertical line test, okay? So that's our 3rd way of testing, and it's the easiest. We're going to look at this in future years. And I'll talk a little bit more about the philosophy of it. Right now, I just want you to understand how the test works. And just know that in the future, I'll explain kind of the theory behind it a little bit more. The way the vertical line test goes is that you draw out a picture of a function. What? Functions have pictures? Yes, they do. And they take all different kinds of shapes. This is one kind of function. It's called a sinusoid, and the older girls are studying it all the time. But here's how you can tell if it's a function or not. You draw a vertical line. I'm going to use a different color just so that it shows up a little bit more. You draw vertical lines through the picture. And here's the rule. It's one of those rules that, and I'm just going to put circles at the place where my pink lines touch the function. Not the graph itself, but the function, right? Oops, I spelled it wrong. Squeeze the N in function. It's hard to say this concisely. Once I explain it, I think it'll make sense to you. Okay, so we drew our function and then we drew some random vertical lines. What we do is we look to see how many times each individual line crosses that function. If it touches the function or crosses the function at no more than 1 point, then this is a valid function. Okay? So there we can see each line is only touching once, right? None of these vertical lines are touching more than once. If we drew horizontal lines, it would touch the function more than once, but that's not the test. The test is only vertical lines. Okay? Now, let me show you a picture of one that fails this test. So this one works. This is a valid function, right? This one's going to be a failure. And we're going to have to make a dead smiley to go with it. All right, ready? It's going to be a circle. A circle is a function. A circle is a, it's technically not, it's not a function. And I'm not going to get into the details of this right now, but it fails the vertical line test because if we draw a vertical line, we get 2 points of intersection, right? Now, granted, if we were perfect, we could draw a line here and it would touch just once if we drew it perfectly. But if you can imagine a line that crosses more than 1 point on the function, then it fails the test, right? It's not if you can just do one, it's if that any line that you draw, wherever you can imagine drawing it, touches it no more than once. Okay, so this one fails because look, it's really easy to see. All right, the nice thing about these problems is that you can do them just by looking at the picture. And we'll do our last example with an A, B, and a C. Just looking at John's pictures, all right? And these are problems that it's fine to do that way. You don't have to copy these over into your book. Okay, A. Do you think A is a function where it touches only once, or does it fail because it touches twice? Oh, well, this is really easy, right? We can see, like, the y-axis is doing it, and that's a vertical line. Touch, touch, touch. No, it's not a function. What about this one? Yeah, this one looks good, right? Because it's curving, but it's curving in such a way that any line would only touch it once. Okay, so this one is a function. What about this one? Again, the y-axis shows us that it fails, right? Because it curves. So, no bueno. So, not a function, yes a function, not a function. Isn't that so much easier to see than our crazy oval test or our pairs test? This one is the most fun of the function tests. The only problem is you have to have somebody else draw the lines for you, or draw the picture for you, because that would be work. But that's the end of part B, tests for functions. A baby step, right? Not too bad. We just add a third way of testing. And this works well when instead of having numbers, we have a picture. Love it. Okay, that is the end of lesson 87. And, oh, I'm spoiling you guys. I'm looking ahead to the next lesson, but that's not fair. Okay, 87 is done. Thank you, goodbye.